Hey folks, welcome to the BIM Forum and Building Smart webinar live stream for today. Excited to have Dion here with me. We have a very active chat going on right now, so it's very cool to see on the side. Um, but I will answer a lot of questions that are coming in, but I just want to get through a few introduction items, a few housekeeping things. So that being said, this is our IFC show and tell. You guys are in for a treat. I got to preview some of it, and I feel like my office chair needs a 4-point harness because it is nonstop. So anyhow, if you're a Key and Peele fan, you know that nonstop reference. Anyhow, um, with me is Gian Molt. He is the emerging digital engineering manager with Lend Lease. He is based out of Australia, so I think we owe him all a cup of coffee or espresso or Red Bull or something for getting up and doing this first thing in the morning. So, or a cup of tea. There's that too if you're classy and not a knuckle dragger like me. But anyhow, great having you here. Dion is also a B arc and an M arc. I guess going one round wasn't enough. You had to do two just to just to prove that architecture school was not ready for you. So great having you here. My degree is in business administration, so which my wife, who's an M.Arch or a B.Arch with a master's in industrial design, she teases me about endlessly. So great having you here, Dion. But before we let you just go off on a tear, a few housekeeping items. Our next webinar after this one is going to be with Tom Zahner. And if you know who Zahner is, they're an amazing metal panel company. They do all sorts of gorgeous facades, making metal panel do things that metal panel has no business doing. So I'm really excited to hear about their case study on SoFi Stadium. I live and work in Los Angeles, so from my big job site over by LAX, I've actually had to look up from our roof at that project being built. So well, didn't have to, but it was a good time seeing another very large project coming up out of the ground. So looking forward to that here just next month. So great to see we got people from Greece, from I think Switzerland, Seattle, Washington, Canada, Ontario, um, Germany, Netherlands, like all over. Um, we do we have the Kingdom of Bahrain in here too? It's crazy. It's a wonderful international group. So thanks for making time for this. If you do have a hot second, please go to bimform.org and do the open standards survey. It's really helpful for our industry to really understand where our standards are and where they need to be headed. Um, and every time I hear the word about standards in the AEC industry, I think of an old joke that a German once told me and said the best thing about standards is that everyone has a different one. So I think this is a fantastic opportunity to continue to have some international standards that are meaningful for the AEC industry. So do your part and do a couple clicks. Some live stream stuff. I I thought I was going to have to tell you to use the chat. Like that's not an issue. You're blowing it up. So thank you. Yes, we are recording it. And yes, it's going to go up on YouTube. You will also get an automatic email at the end of the live stream that will have a link to watch later. So if you've registered, which is how you're here, you'll be getting that email automatically as well. Otherwise, you can just go to YouTube and check out BIM Forum USA. Last time I checked, right before the live stream started, we had a grand total of 9 subscribers. So if you want to see automatic updates on when we have a new live stream going up or a new live stream occurring, that's another way to do it. And who knows? I guess we've only been doing it for 30 days, so 9 subscribers in 30 days. 30 days, I guess, isn't terrible, but hey, feel free to light us up. Okay, now that being said, Dion, it's time for you to take it away, and I'm gonna stop talking. I'm gonna get my popcorn and sit back and watch you do your thing. So thank you.
Today's talk is going to be a very fast-paced introduction to OpenBIM and open source. We're going to cover 4 topics. First, we'll describe traditional BIM workflows and how native IFC is different. We'll then look at some pretty pictures demonstrating what you can do with native IFC. Then we'll take a quick break and have a detailed technical discussion about how IFC actually works under the hood. And finally, we'll end with some software demonstrations, and we'll see how free and open source software is changing our industry and where you should learn more. Let's start with traditional BIM. So BIM promises the ability to describe our built environment using objects with relationships and properties just like in real life. So in theory, a door in a BIM model can contain its physical shape, its annotative symbol, materials, manufacturer, warranty, and also complex relationships like when it will be built, who's building it, how much it costs, its environmental impact, and more. And BIM promises this holistic information model that helps all disciplines make informed, wise decisions to design a better built environment. But this promise is not the reality that we see today. Today, the average BIM model has data that is piecemeal, it's unstructured and untrustworthy. And during the design and construction process, we don't have this single continuous holistic model. We have multiple, isolated, discipline-specific models. And these models are discarded and rebuilt at each project phase, and models duplicate one another. And traditional BIM authoring tools like Revit and ArchiCAD don't use open data standards. So the data Revit uses to describe a wall is different from how ArchiCAD describes walls and so on. And this problem is much deeper than just being difficult to import or export. It means that every project describes geometry in a different way. It puts common metadata like fire ratings or wall type names in a different location. And the data sets are isolated per discipline model. And that's because these traditional systems were never designed to capture the relationships across the disciplines. So the BIM we're all doing now is not much better than a SketchUp model plus a spreadsheet, because everybody's spreadsheet template is organized differently. In fact, traditional BIM is worse than spreadsheets because, at least with spreadsheets, anyone can access a spreadsheet, but our BIM data is locked into proprietary formats. Right? Spreadsheets don't expire, but old BIM models can't be opened with current software. You also don't need to pay a subscription fee to open a spreadsheet, but most BIM data is rented from vendors through subscriptions. Spreadsheets can also work across any discipline, but most proprietary BIM data structures are limited to a single or maybe 2 disciplines. Spreadsheets can also be customized, extended, and scripted, but our BIM data is only limited through proprietary black box APIs. Right now, proprietary data systems dictate what we can and cannot do with our tools, not our industry. If we were to ask ourselves, what would be an ideal digital design, engineering, and construction workflow, our answers are constrained by what the software vendors tell us. And this problem is not isolated to a single discipline or a single technology. It's a systemic failure in our digital collaboration. Our systems are just not designed to collaborate, and it doesn't have to be this way. If we adopt international standards and collectively invested in open source software, we can design our own digital pipelines, just like the IT or VFX industries that have already made this transformation before us. So when BIM technologies were first developed, there were no data standards available for the industry. Each company invented its own proprietary data dialect, and each dialect can't communicate across different technologies. In the mid-1990s, the industry recognized this problem. An industry consortium was formed and developed an international BIM data standard called the Industry Foundation Classes, or IFC. And IFC was designed as a digital language to describe our built environment. It describes things right from structural analysis right through to smart building sensors. It's a well-established international ISO standard, and there are freely published open data specifications. The development is vendor neutral, it's platform and technology independent, but most importantly, IFC is the only data specification available today that integrates all the disciplines in our industry. And most of us use IFCs by sharing 3D models, right? We create these IFCs by importing and exporting from traditional BIM applications. But whenever we press the export button, we know that half the model data and intelligence is lost. And because so much data is lost, we treat these IFCs just as a 3D format with some metadata tags. We don't really know what data is kept, how it's kept, and so these superficially produced IFCs from traditional BIM is really only a read-only snapshot that nobody really trusts. So after 25 years of development, after IFC has been integrated into hundreds of software and their developer libraries for a wide variety of programming languages, and there's multiple serializations so it can work through files or APIs, what have we achieved? After all the contractual requirements for OpenBIM, their certification, training, and user guides, why do we still have all these problems? And the answer is that nothing has fundamentally changed. We're still using proprietary data platforms, and these proprietary systems are still based on a historic, unstructured, unstandardized proprietary data dialects that cannot communicate with other systems. So today, I want to go further and talk about native IFC. So instead of translating into IFC from traditional BIM, we can now directly author IFCs natively without any imports, export, no data loss, and no model linking. So translated IFCs have artificial limitations imposed by proprietary systems. So I'd like to show you some examples of what you can do with native IFC. Here's an image of my living room back in 2019, and this image is quite special because it's not a photograph. It's actually a render of an IFC model, and every object you see is classified into IFC object types. It has enough metadata to be scheduled with detail down to every individual blade of grass. And this is considered over-modeling with traditional BIM tools, but it's actually quite average if you use CG software instead to create your BIM models. This render is also special because it's not an artistic render. It's a photometrically correct, validated light simulation using material data stored in the IFC itself. So there's no test renders, no lighting adjustments, no color pickers used. It's just pure, rich IFC data with numerical physical measurements from product samples. This is rendered using the free software Radiant, which is the gold standard for lighting simulation. So the image shown on one side is the simulation adjusted for the CIE average human eye, and the other is the photograph. So with native IFC, your BIM model can store the data required for validated render outputs, just like this. Here's some derived work by somebody online who then took this simulation and extended it. He does thousands of simulations to cover every frame taken from a head-tracked VR environment and calculates the daylight glare probability and vertical illumination for lighting engineers. So here's a luminance simulation with the false color values on the right. IFC also supports point clouds. Here we're taking measurements off a construction site. So semantically, it's not just a bunch of points. These points are actually assigned to BIM objects. So if you're looking at as-built verification, heritage, or model archival, the IFC data and the point cloud scans can integrate. You can also generate drawings from IFC. Here's a Revit sample model taken out into IFC, then fully annotated and documented using native IFC. So there's no Revit or AutoCAD, but just pure native IFC for all the grids, dimensions, labels, and so on. Other software in our industry create 2D drawings using proprietary formats such as DWG. Other derived formats like DXF, DWG, and PDF also miss out on all of the BIM data. In contrast, what you're looking at here is the Open SVG format, which means that anybody can open it on a standard web browser on your tablet or your phone with no special software restrictions like DWG has. SVG also supports semantic metadata, so we can store IFC data in the SVG. So if I have a 2D rectangle on the plan, It knows it comes from a 3D object with material properties and tags. So just by generating a single plan, a viewer can interactively display different properties with different hatches, symbols, or labels on the fly. There's no need to spend hours shuffling around tags on a sheet because your viewer can dynamically generate them. And being native IFC, this means that our drawings now become programmatically queryable. In the same way that you can write scripts to query a model, you can now write scripts to query 2D drawings even after they've been published. So imagine on site, on a tablet, we can click through markers and labels on fully interactive drawings, which can go back and forth between 3D and 2D and auto-generated schedules and specifications, attached BIM documents, and using completely free viewers that worked in a regular browser on any device. This could be the future of drawings and diagrams if we switched away from proprietary DWGs and moved towards open data standards. Native IFC also supports structural analysis. It supports all the information you need to create analytical models with boundary conditions, load cases and combinations, and structural members. It can be linked to any structural engine you wish. And once the simulation is performed, the results and the reaction forces can then be stored back in the IFC. So in these images, the structural analysis was performed using an open source software known as Codaster, but there are other tools that can be used too. The AdaPi software lets you use high-level code to describe structural IFC components, and these components can be visualized and analyzed both in Codaster and Calculix, another open-source structural analysis package. Here's an example custom workflow where the user sketches and traces walls which are then converted into IFC walls. So here's another example where a scene is sketched in 3D and you can view it in a VR environment. And because even though these are just rough sketches, it's still IFC, so it can be annotated and scheduled. But it still gives you the freedom to think in non-manifold geometry. So here you can see the same scene brought into Revit through IFC. And in this example, the building is generated. So the user can draw boxes of these non-manifold spaces, and with some topological analysis to determine the space connectivity, it can generate whole buildings and cities. And so the resultant spaces know their spatial function, and all the walls, doors, and windows are natively stored in the IFC. This actual same approach goes through an evolutionary solver to start scoring the spaces with respect to the values in the architect book pattern language. And the software we're showing here is actually a combination of 3 free software: Topologic, Homemaker, and the Blender BIM add-on. So Topologic provides the topological analysis of the geometry, where you can determine whether spaces are connected using code. Homemaker then uses Topologic to generate designs in native IFC, and the Blender BIM add-on then helps visualize and use Homemaker to modify these IFCs. And then there are buildings designed completely open source. So here are some projects which are designed a little bit like Wikipedia, where everybody can edit it. So here's a recent residential project by the Opening Design Studio, and you can see all their 3D detailing, which uses native IFC exchanges and a workflow using Git. Native IFC also supports costing completely integrated into the model with formulas and derived quantities. So you don't need to export models or link models or map the models. You can just directly create your cost schedules within the model alongside your design team. And even more complex operations like automatic formwork calculations can be performed and recorded directly in your cost schedules. And the scheduling can also be done with native IFC in a similarly fully integrated manner with no exports or linking. You can create calendars, work schedules, task dependencies, and calculate critical paths, float early, late dates, recorded versus actual. And naturally, we can also visualize the progress or generate animations. And all these animations were generated directly from the IFC. So if you update the model or the schedule, the animations automatically update alongside it. There's also automated model checking, project asset libraries, classification system integration, design constraints. But I don't have any pretty pictures for those, so we'll skip over this stuff. So how does native IFC actually achieve all of this? IFC describes a series of concepts that have meaning in our industry. And each one of these concepts is known as a class, and that's how the industry foundation classes gets its name. So for those who know programming, this is very much like classes in programming. And for those who don't worry about it. So just think of a class as a concept. And each class has a definition provided as part of an international standard. And these classes have attributes to give information about them, like name or description. And some of these attributes refer to other classes, so classes can be connected using relationships. And some of these classes are semantically meaningful to humans, and some are a bit more like raw data that makes sense only when combined with a semantic class. And when you put all this together, this is known as the IFC object model, and you can query and generate output from it. So any software can create and describe BIM concepts using IFC classes with any programming language. And if you want to transfer or store some of these classes, you can serialize it into one of these formats. And the one most of us are familiar with is the .ifc file, and this is a plain text step-based serialization, but you can also use XML, JSON, and binary. Or you might not even use a file. You might use a relational database or a graph database, or just something purely in memory and access it through an API and exchange snippets of JSON or XML. In total, there are nearly 1,000 IFC classes, and we won't have time to go through them today, but I can provide a high-level overview and pick out some classes as an example of what's possible. And because there's so many classes, the definition of these classes are categorized into a hierarchical tree, and this groups together similar classes. And when you group them together, this means that they inherit all the attributes and the relationships of their parent classes. So you can think of this tree as a dictionary of IFC classes, and you can see this full list on the Building Smart online documentation. And this dictionary is written in a computer language known as Express. And the definition of each class under the hood looks a little bit like this. And because the dictionary definitions are written in a computer language, this guarantees that our digital tools can speak it consistently. And this tree is really great for computers to understand because it represents when the attributes and the relationships are inherited. An alternative way to categorize IFC classes is into 4 main groups. And these groups then have more subcategories within them. And these categories are designed for different audiences to understand. At the bottom, we have the fundamental building blocks, like the classes that represent geometry. And at the top, we have high-level categories, which are most relevant to specific disciplines, like HVAC classes, or electrical classes, or structural classes. And in between, we have classes that are shared across multiple disciplines. And for some people, they prefer to browse the dictionary of classes via an alphabetical list. Some like to look at it as a hierarchical list, and some like to look at it using these categories. And there's no right or wrong. They're all just different ways to navigate through IFC concepts and will appeal to different people. And although this dictionary is a great reference of all the classes and concepts in our industry, a dictionary only tells you the meaning of words, not how to construct sentences. If you want to describe scenarios in our built environment, we need to combine the classes together using a mutually agreed approach. So to understand how to combine classes meaningfully, there are a series of fundamental concepts described in the Building Smart documentation. And here's the chapter to read more, but today I'll focus on 3 simple concepts to describe and give you a taste of what's possible. The first concept is the IFC project class. When you're describing a BIM project, you must define your project using the IFC project class. Once you've defined it, other classes may be related to your project directly or indirectly. So this means that the project is the entry point for all software to start looking for data. This is a bit like reading a book. You always need to have a first page to begin reading. So let's view the documentation for the IFC project class. You'll find some translations for the class, a changelog of modifications, ISO definition, the categorization within the hierarchy, and its attributes. So if we click on Attribute Inheritance, you'll find that IFC projects have 9 attributes, which you can see in the first column. The name, the data type, and the description of each attribute is shown. The cardinality column tells you if the attribute is optional or if the attribute can contain more than one value. And because the IFC project concept is so fundamental, you'll find it in every IFC file that you have. And because the IFC files are plain text, just open it in any text editor, and you'll find something that looks a bit like this. You'll see that every line represents data from a single IFC class. Each line starts with an identifier, the name of the class, followed by a comma-separated list of all the attributes. So if you search for IFC project, you'll find a line that describes the IFC project. And in this case, the identifier is 11, the class name is IFC project, and here are the 9 attributes shown in order. The name of the project is 123 Foo with an object type of residential. And to read these attributes, you can see that the string values are single quoted, numbers, integers, and decimals are not. You have null values represented by a $sign, and you have references to other classes using a hash prefix. The enumerations are pre- and postfix with a period. So let's see an example. This IFC project has a units in context attribute referencing another class just below. This then represents yet another class which defines an SI unit, stating that the linear dimensions of our project are recorded in millimeters. And if you spend half an hour every day before bedtime reading 10 lines of IFC, it'll sort of make sense within a week. And if this step format looks really scary to you, here's actually all the same data in JSON. Another concept is spatial decomposition. Spatial decomposition is how IFC describes how larger spaces break down into smaller spaces. You can use this concept on any IFC spatial element class. So remember that dictionary tree of IFC classes where classes inherit attributes and relationships from parent classes? In the dictionary, IFC spatial element has many subclasses, so this concept equally applies to them. So let's say I've described an IFC site and an IFC building. We can use the spatial decomposition concept to create a relationship using a third class known as IFC rel aggregates. Now, the IFC rel aggregates class has 6 attributes. 2 of these attributes can refer to other classes. Specifically, the relating object attribute refers to larger things, and the related objects attribute refers to smaller things. So if I reference my site and building accordingly, I've essentially described that my building is situated on the site. And I can repeat this pattern again and again and again to create a tree of spaces and stories, wings of buildings, multiple buildings and sites and roads and traffic lanes and so on. Here's another simple, fundamental concept to describe material associations. So let's say we want to say that a slab is made out of concrete. We can use an IFC slab and an IFC material class, and we connect them using an IFC rel associates material class. So just like the IFC rel aggregates class we used in the spatial decomposition concept, you'll notice that both classes contain the word rel, and they're all used for relating things together. So here the IFC rel associates material class has 2 attributes which we can use to connect our object with our material. There are a lot more concepts we can't cover in detail, but we'll skim over a few more just to get an idea of what's possible. So here's a simple concept which describes how a work schedule can contain tasks. And of course, this is used in construction scheduling, but it's also used in facility management. In construction scheduling, a work schedule is a collection of tasks that must be completed over a specific timeline in order to reach the final deliverable of the project, such as constructing and commissioning a building. We can extend this concept with this one, where tasks can be linked to objects in the BIM model. And in this concept, our task is set as a construction task, which means that the task results in the wall being constructed. Tasks can also have sequential relationships. So in this scenario, a predecessor task, which is setting up the former, has a finish to start relationship to a successor task, and it has a lag time of 1 elapsed day between them. And these concepts are quite straightforward, but some concepts are very difficult to understand. I'll show you an extreme example. So there are concepts which describe details about implicit and parametric geometry, such as for rail alignment curves. And this requires a detailed understanding of computational geometry to appreciate. Other concepts are broader and more intertwined, mixing disciplines such as for costing, scheduling, resource management, productivity rates, and performance histories. Here's a really complex diagram showing all the interdependencies and relationships between costing, scheduling, and resource management. But the good news is that the majority of the concepts you'll deal with are pretty straightforward, and the difficult ones have already been resolved for you by software developers. There are over 100 concepts described in IFC, and I've only explained 3 basic ones and skimmed through a few more, but there are so many I won't have time to go through today. But I hope you can see that IFC can be incredibly rich in data, and it applies across many disciplines and offers more than what we're currently doing to digitally describe our built environment. And it's an incredible industry effort to standardize and localize the immense amount of interdependent data that we work with. And right now, our industry is like the early days of the internet, where websites mostly work with certain browsers but not others, and the shared protocols and languages of the internet were still being formed. So I hope you can see how closed data, vendor-specific APIs, and lossy data translations through imports and exports is just not the future. The future is when our foundations all natively speak the same digital language, formed through mutual industry agreement. And it took a long time for the internet to get to where it is today, and that's from the most digitally savvy industry, the IT sector. Our industry is divided and diverse, and it's only slowly catching up to the norm in other digital systems. So we really need to work together. So a common myth I hear about IFC is that it's like a PDF for BIM data. And this is only partially true. Most of us use IFC like a PDF file, and proprietary vendors tend to treat it like a PDF, but this is changing. Thanks to free software, any user can now move away from traditional BIM and start taking advantage of the full breadth of capabilities of native IFC. And these capabilities have been specified in the international standards since the early 2000s, but only now is software catching up to it. So you can treat it like a PDF, but it's designed to be so much more. So in theory, you can ditch Revit today and write all your BIM using Notepad. And writing your BIM models with just Notepad is actually an excellent way to learn OpenBIM for those of you who are up to the task. And in fact, that's how I learned how IFC worked. So if you're up for the challenge, I highly recommend it. But for today's talk, we're not going to do that. And I'm going to introduce some open source software to work with IFC called the Blender BIM add-on. And it's free and it works on all platforms, so everyone can try it out. The Blender BIM add-on started back in 2019, and we were modeling a small building in Blender, and it had lots of complex geometry. And it came to a point where we needed to start documenting, scheduling, and assigning data. And we had two choices. We could either rebuild the model with traditional BIM tools, or implement IFC into Blender. And we took a leap of faith, and we wrote 83 lines of code that exported Blender geometry into IFC. And this was pretty exciting for us. And those 83 lines of code grew into a digital engineer's Swiss Army knife to work with IFC. And a month and a half later, we packaged it for the public, and someone picked it up. And they used it to visualize compactor machine data to build a highway. Now, obviously, visualizing compactor machine data isn't top of the list of features when you're developing a BIM app from scratch. But it goes to show it's not about vendors delivering a product. It's about users collectively building an ecosystem of utilities that you can repurpose to build the tool that you need. And since then, IFC OpenShell and the Blender BIM add-on has won the Building Smart Technology Award. We've received an Epic Games Mega Grant, a Cesium Ecosystem Grant, and annually participated in the Google Summer of Code. It's also now being used in various workflows, from end-to-end delivery of small architectural projects to more specialized tasks on huge projects like hospitals, train stations, and perhaps the biggest rollout yet being the Hinkley Point C nuclear power plant in the UK. There's also a number of universities teaching this and hundreds of results in academic papers. So here's an example of a small building being modeled natively in IFC with the Blender BIM add-on. So we're directly creating IFC walls, IFC slabs, IFC doors, IFC spaces, and so on. And we can generate drawings, we can cut floor plans, sections. We use IFC annotations for dimensions, IFC documents for drawings and schedules. And what you'll notice is that it's really not that different from the tools that you already use. We're creating elements from a library of construction types, parametrically layered materials, and standardized profiles. Here's an example of a small architectural project by Opening Design, delivered end-to-end with native IFC using the Blender BIM add-on. This involves modeling, drawing and documentation, and visualization. So using IFC as a native format doesn't prevent integrations or extensions for highly parametric or bespoke modeling. IFC contains basic parametric doors, windows, layered and profiled elements, pipes and ducts, But we can also support more complex scenarios like parametric assets, stairs, roofs, and visual scripting. So here's something a little different. In this tutorial by Sigma Dimensions, we can see creating an availability calendar and construction work schedule directly in native IFC. You can see different task relationships being created, like finish to start, start to start, and so on, lag times being created, and naturally the 3D modeled element can be related to tasks as well. And IFC also supports the construction resources. So he's storing the cost rates, the productivity rates for labor and equipment, and these can be parametrically linked to the schedules, so the task durations can be calculated from the labor productivity. And this would also update any cost schedules that are linked to, and you can start balancing cost, time, and resources. And of course, you can visualize this with a variety of colors, animations, and Gantt chart styles. And in this demonstration, we're looking at distribution system connectivity. So IFC understands different system types and subsystems. It knows when ports of different equipment can be connected to one another and the direction of the distribution flow. You can also link it to sensors and time series data for live sensor data with external libraries or open source schemas like Brick Schema. And in here we can see this incredible technical demonstration by Bruno Poffel about the IFC Git integration. And here we can see multiple people around the world collaborating on the same IFC model for the first time since being introduced to this feature. Modifications can be visualized, and simultaneous changes to different and same parts of the model can be reconciled into a valid IFC graph. I'm only showing a tiny portion of what's available with native IFC. Here's a taste of some of the other utilities in the IFC OpenShell ecosystem. So whether you're generating asset register spreadsheets using Kobe, or doing visual scripting with Sverjak, or clash detection, there's a lot more to cover. And we also haven't gone into detail about complementary schemas like model auditing using IFC Tester, or model coordination and review with BCF, or standardized property set templates and classifications with the BSDD. For the programmers in the audience, IFC OpenShell is available in C++ or in Python, and there's also a technical preview of a WASM implementation to run on a web browser. It's available on command line and graphical interface, so you can build these headless server workflows for your BIM models. So here's a simple example of how to create a native IFC from scratch. We'll create a blank file, create a project class, we'll define some units, and we'll add a new building. We'll spatially insert our building inside the project. We'll create a slab, a roof, and the 4 walls, and we'll put our building elements inside the building, and that's it. We have a minimal BIM model in 15 lines of code. Our documentation covers this and a lot more in more detail. And the reason we could build a BIM model so quickly is because IFC OpenShell offers a high-level API to manipulate IFC. And this API is unique in the industry. It's the only tool that comprehensively offers native IFC manipulation via code across 40 different modules that tackle everything from geometry, 4D, 5D, structural analysis, and more. And all of the API calls are high-level, so the details like purging the subgraphs, handling IFC version differences, ownership tracking, date-time conversions, and so on, they're all resolved for you. The IFC OpenShell system is also unique that it supports transactions, so you can undo and redo operations. This is used by the FreeCAD project, ZeoKit, BIM Server, and many other applications in the industry. So here's the IFC that we just created and opened in the Blender BIM add-on. And you can see the project and the building and the other elements inside it. And our 3D scene is empty because we haven't created any geometry. But the data attributes are still coming through correctly. So let's select the data and let's add some standardized metadata about a lease agreement. We can also use the IFC CSV tool to export a spreadsheet schedule of all our walls. Let's edit the spreadsheet and we can re-import the changes back into the IFC. And you can see we're very quickly auditing and editing the IFC data in bulk. And what I'm showing you is that you can mix and match tools to suit your workflow. So here's another example. We're going to do the exact same thing, but with code to bulk edit data with using spreadsheets. And in this example, we can use code again to automate the generation of a construction sequence. And you can visualize it in Gantt form or animation form. And here's a simple overshadowing study done live on the top. So even if you don't know programming, I'd like to walk you through a very simple example of using code to interact with IFC. So Blender comes with Python pre-installed, so you don't need to install Python. It comes with an interactive Python interpreter, and you can run full Python scripts. And of course, if you want, you can install everything separately and run it on its own. But if you use Blender and the BlenderBIM add-on, this can get you up and running in about 5 minutes. So let's activate the built-in Python interpreter in Blender and run some code. And if you don't know what you're typing, you just press Tab, and it auto-completes with some suggestions. And right now with AI, you can ask it to help you write these simple scripts. And if you don't know Python, the basics are on the right-hand side of the slide. So the module in Python that provides all the functions to interact with IFC is known as IFC OpenShell. So to use it, we'll type import IFC OpenShell, we'll press enter, and now when you type IFC OpenShell followed by the period and press tab, it will autocomplete showing you all of the available functions. So the function we want to open an IFC file is called open, and you can see it returns an IFC object, which you can store in a variable. And if you tab into that variable, you can see all the functions we can do on the IFC file. So let's say this is the IFC that we just opened. And of course, every IFC class is on a new line, and there's an ID number at the beginning. And the project class ID is 11. So to retrieve data about the IFC project, just use the byId function of IFC OpenShell, and this will give you back a project object. And if you tab into the project object, you'll find all of its attributes. And if you type the name of an attribute and press enter, you can view the attribute. So here's the full script so far just to get the project name. And it's 4 lines of code. Now I've experienced that about half the models have actually got the project names wrong or inconsistent. So with just 4 lines of code, you can automate a project name check. If you wanted to check all the information about an IFC class without needing to look up the attributes, just use the getInfo function. So having to know the ID of the IFC project class is actually quite inconvenient. So if you know the global ID instead, you can do that too. But if you don't know the global ID, you can simply search for all the IFC projects in your data. So here's a simple example to search by IFC class. And let's search for all the wall type classes to find out how many wall construction types are defined in our project. And let's print out all the names of our wall construction types. And almost every single BIM project that I've come across has incorrectly recorded the names of their construction types. So let's fix it. And this is all it takes to improve the quality of your BIM data. Once you're done editing, just save your IFC file. It's quick, it's easy, and especially with the help of AI now, anyone can do this. I'd like to stress that everything I've demonstrated so far is only alpha software. There are many incomplete features and bugs, and this is a work in progress representing the leading developments in the field of OpenBIM. So it's not yet a drop-in replacement for the more entrenched traditional BIM tools, but it's slowly growing. And that said, I hope you're excited by what you see and you can see its potential. And there are over 150 developers who have volunteered to contribute to the software, and it's starting to reach a point where you can deliver a small architectural project end-to-end in native IFC. And we also know that it's playing various roles on larger projects, not for end-to-end delivery, but in auditing, fixing, and certain bespoke systems integration that these larger AEC firms tend to be capable of. So the IFC OpenShell and BlenderBIM add-on software that's been showcased throughout this presentation is completely free and open sourced. And that's important because today's talk isn't just about cool technologies. It's also about a cultural shift that our industry is going through. And this cultural shift is known as a free software culture. And the term free software, it's got nothing to do with the cost of software, the money involved, but it's specifically about 4 types of freedoms for the users of software. And this means our own freedom as industry professionals. The first freedom is that we must be able to use software for any purpose. Secondly, you need to be able to study and modify the workings of the software. So if the software doesn't do what you want it to, you can fix it. Or if you want to understand why things are the way that they are, you can investigate. The third freedom is that you can redistribute the software. So if somebody doesn't have access to these tools, you can share it with them. Our industry has a huge disparity in its digital adoption, and this unequal access makes it difficult to achieve industry goals of smarter cities and level playing fields. And fourth, whenever you make any improvements or changes to the code or the way the software works, you can redistribute that change to the public. So if 10 people from 10 companies make one improvement to improve the efficiency of something like cost estimating or carbon counting or structural accuracy, the entire world benefits. And this is an incredible multiplier effect to benefit our industry. And what you'll notice is that there's some similarities or parallels between the objectives of OpenBIM and the culture of the free software community. But the focuses are slightly different. OpenBIM focuses on the freedom of data, whereas open source focuses on the freedom of users of the data. But the end goal is quite similar. It's about a culture of collaboration. And we need both sides of this coin. We need a strong technical foundation of open data standards, but we equally well need users who are engaged and empowered, and they have to be in control over their own tools. And this is because it's important that it's us, the users, who are driving the development of the industry's data, because we provide the grassroots insights that maximize the industry benefit of these standards. It's not appropriate that the benefits of our data are filtered through these lossy imports and exports. It's not appropriate that we're stuck to using proprietary systems and black boxes. And it's not appropriate that progress is driven by commercial interest rather than industry interest. I'd also like to highlight that this is not a new thing. Free and open source software has had a long history of creating fundamental changes in our industry. So back in 1984, the GIS industry had exactly the same problem. There were a number of proprietary systems that were just not designed to collaborate. And so the GRASS GIS project was created. There was an open source toolkit to improve interoperability. And from this initiative, we get the term OpenGIS. And the Open Geospatial Consortium was formed, and this helped develop many of the open data standards that are fundamental to the GIS industry. And there are many open source projects developed under this umbrella, like OpenStreetMaps, which help provide free and open GIS data to millions of users. The majority of building physics simulation is also provided by free and open source software. So for example, Radiance is the gold standard for light simulation, and Energy Plus is used for energy simulation. There's also OpenLCA, which is increasingly adopted for life cycle analysis. In fact, many of the concepts that we take for granted in 3D rendering were developed by Radiance, such as the HDR format, sun and sky settings, exposure control, the physical camera settings when rendering, and even things like the normal map for texturing. This was pioneered back in 1992 by Radiance. Ladybug tools help package these engines, and this has completely changed our industry. It's brought environmental simulation to the masses. And this pattern happened again with open source software like Blender, which provides access to mesh modeling, computational design, and visualization to everybody. And FreeCAD is doing the same for parametric solid modeling, industrial design, and computer-aided manufacturing. And a similar shift is happening right now with BIM. Open source software libraries like IFC OpenShell, XBIM, and IFC.js now allow anybody to build their own BIM software that's based on the cross-discipline research and data structures developed over 25 years of industry experience. These open source libraries are already used in academia for the latest in BIM research and teaching, and it offers advanced capabilities far beyond the proprietary solutions. The open source architecture community also maintains a directory of over 100 free software currently being developed that are related to our industry. They also maintain a directory of libraries to build your own software. And I've only had the opportunity to demonstrate just one of these today, but hopefully I've shown that there are many incredible communities out there trying to do better. And one of these communities is known as the Open Source Architecture Community, or OSArch. And this covers all disciplines, not just architecture. And it's a fantastic entry point to discover just what's out there with resources like forums, chat rooms, Meetup, Wiki, and more. It's a community of industry professionals who understand that working with our built environment, it's a complex task that no single person, company, discipline, or country has the answers. And by sharing together, we can make a better world. And these changes are not easy, they're not fast. It's a foundational change that relies on a native digital literacy of the entire industry to speak the same digital language. It's a change that relies on a culture of sharing ideas and solutions freely for everyone's benefit. A culture that understands our industry is not about digital tools. It's about a physical world. And the virtual environment that we're designing one day becomes the physical environment that we all live in. So as the explosion of new technologies continue, our industry is shifting away from a vendor-centric approach to a native open data approach. And this comes with an ecosystem of interoperable, free open source software. Imagine how different our industry would be if we invested in this accessible open source system 10 years ago. But now is the chance for all of us, large or small, whether or not you can write code or implement policies or teach or do research, everyone can make a difference. So by working together, we can build a new digital built environment that we have full control over. So let's change the industry together. And thank you for listening.
That was intense. That was a lot. I don't know that we had a few questions come in the chat. But I had a few of my own. Um, I mean, okay, so this is more of a reflection than it is a question, but it really hurt, man, when you said that BIM data is rented, because it's so true, right? Like, if we stop paying for our software, we kind of lose all of that historic information that we've created over so many projects. So that landed and it stung a little bit. I don't know if anyone else felt the same way, but wow. Um, so one question that I had was like you've shown a bunch of tools. A lot of them I thought were focused on buildings, like and absolutely incredible if you think about where Open BIM and where IFC was like 10 years ago to where it is now. Um, it's really incredible how the tools and how the entire landscape has changed. But related to that, for civil, the civil scope, like site, let's say roads, topo surface, underground utilities, is there a tool or a workflow that you would recommend? Because I feel like that the civil engineers have all been left behind with, at least in the United States, some really um, antiquated tools like Civil 3D. It's essentially like, AutoCAD with stuff. What do you think?
Well, full disclaimer here, I don't design horizontal infrastructure here. I've never done horizontal construction. Um, and yes, they have been left behind, absolutely. And I think that's one of the main efforts in IFC 4x3, which is the upcoming version of IFC, is to help introduce the civil world back into IFC. So that includes improved geolocation. Uh, it improve it improves geometry for things like rail alignment curves, or road alignment curves, and it introduces a whole set of new infrastructure-related out-of-the-box classifications and properties. So I think it's acknowledged that yes, we are the whole industry is behind in that aspect, and we're slowly taking steps to solve it.
That's it's exciting. It'll be great to never work on a project where I don't have a three-dimensional topo surface ever again, let alone one that was designed in software that, had its origins before I was even born. Um, let's see. There's some great questions here. I'm gonna just push this one to the live stream because it's a lot. I don't want to read that out loud. Um, did this question make sense to you? Because it sounds like if I was to summarize it, they were looking for a way to have some bidirectional communication with an IFC when the work order software won't support a write back function.
Yeah, so this is exactly what we're trying to solve, right? I mean, if you think about it historically, let's say you're not using IFC, you're using a proprietary data schema. The project is finished and you deliver it to the building owner. The building owner most probably doesn't even have software which can view your proprietary data. And they certainly don't have somebody sitting in a corner maintaining their real estate portfolio of 50 buildings, pressing the Revit upgrade. Sorry, I shouldn't have mentioned Revit there, but really that's what yeah, that's what you'd
Yeah.
expect people to do otherwise.
Yeah.
And and IFC now gives you the option that yes, now with an open data standard, and especially once you tack on all of these open source solutions on top, you now have the freedom to go and build these new integrations that previously wasn't possible, and you had to wait for the blessing of a vendor to say, okay, now you can do it. Whereas now you don't need that blessing; you can just do it yourself. So IFC does actually support work orders. It supports IFC tasks, both performed tasks and scheduled tasks, and supports things like a work order approval as well, and a listing of organizations such as the people providing the work, doing the work orders, people approving it, the people who's manufacturing, or the warranty providers. So IFC does support those concepts, but absolutely, there's not many people taking advantage of that. And again, this is something which I think we can see where we were in the past and where we are now and where it's headed. And we are moving towards the ability to do this. So, for example, um, COBie 2.4 talked about a lot about preparing data for that handover state, which could then be loaded into things like these building management systems like Maximo and so on. And COBie 3.0 is actually trying to push that a little bit further. It's a bit of a different beast than 2.4, but one of the things that 3.0 tries to do is it actually tries to be used during the maintenance of the building as well. And for those who don't know, COBie is based off the IFC schema, so all the concepts in COBie can be done in native IFC. So yes, the answer is there's probably not a package solution which does it right now. By all means, go and knock on your vendor's door and say, hey, this would be nice if you did it. Or start to build it yourself. It's actually not that tricky depending on, well, obviously if you've got a huge thing you're maintaining, maybe don't jump just yet, take that leap, but you can start small.
We got Leon asking important questions here.
Absolutely. So that's my rabbit in the background, the Blender BIM rabbit. Her name is Cinnamon. She's super cute. And rabbits do this thing where if they're super chill, they do a flop. So it's like somebody, like they've been shot with a bullet or something. They don't gracefully curl up like a cat or a dog. They just, quunk. And that's what she's doing right now.
It sounds like me at the end of the day. Just fall asleep somewhere.
Yeah,
Awesome.
very adorable.
So let's see. We had a few other questions come in, and I think you may have answered this one.
Yeah, so I think historically the only CDE which does this a little bit is the BIM server software. It's not exactly the prettiest thing out of the box. It's more a technical demonstration, I feel, rather than something that's so polished compared to the other CDEs out there.
And CDE, for the mere mortals, that's a common data environment.
Yeah, absolutely. And just a quick mention there, they talk about Blender being transformed into a CDE. And I think that one thing I'd like to highlight is that everything you saw there in the presentation, Blender is just one interface. The system that talks to IFC and does all the IFC authoring is actually separate from Blender. So you've got IFC OpenShell and you have Blender over here. And because they're separate, that means you can actually take the system and you can go and plug it into a web browser. You can build a CD off the system, and it's the same functions that powers Blender. And in one end, you have a 3D app, you're orbiting in 3D and clicking things, and the other one, you're in a web browser looking at a bunch of links in a spreadsheet. and they're both speaking to the exact same engine or exact same language. It doesn't even actually have to be the same engine. And that's the beauty of native IFC, that if somebody builds a CDE based off XBIM and C Sharp, or based off JavaScript with IFC.js, it will just work. It doesn't matter what you build it with. So that's the beauty of it. And I know quite a few people who have already built these types of CDEs, although they seem to be private internal ones, and I'm a culprit of that as well. I think we've got one for our company, but yeah, absolutely.
We are we are running out of time, but not out of questions or fun. Um, but I'd love to throw one last one in there, which is just a question of performance. Like I think a lot of folks, at least in the United States, have an IFC experience that revolves around just importing IFCs into Revit, where you're at the mercy of how Revit chooses to interpret it, which is usually quite poorly. Um, and the resulting model is usually completely generic features, and performs quite poorly. Um, it was a little bit hard to tell because I think some of your Blender animations were maybe sped up a tiny bit. Um, Either that or you consume more Red Bull than I do. Um, but anyhow, how does it work on a large IFC where you're using a non-traditional AEC tool as your model authoring platform?
Short answer is not well. Not well right now is the slightly
Hmm.
longer answer. And then the even longer answer is that there's quite a few moving parts here. And we haven't solved all of them yet. So, for
Hmm.
example, for a small architectural project right now, you can do an end-to-end project delivery, and it's not quite as polished as the proprietary tools, and we are certainly lagging behind proprietary tools, which have been hacking at this for decades now,
With
um,
billions of dollars worth of
with
funding.
billions of dollars and so on. Yes, but right now there are some crazy people out there, of which were showcased today, uh, which are actually, doing this and delivering commercial content with it, even though it's far behind. And performance-wise and collaboration-wise, they're doing it. They're producing drawings and sections and so on, and they're using tools like IFC Git to collaborate so that they can multiple people editing the same project at the same time. And it's fascinating. And if you're the type of daring person who wants to do that, yeah, go for it. Um, Now, and then you have the opposite side of the coin. You have the big enterprise users, the people working on huge, huge, huge projects, which I do in my day job. And in this regard, it's a bit funny. We're actually way ahead of the game when it comes to these kind of acupunctural digital workflows, like things like model auditing. It's blazing fast. It's really sophisticated. Things like debugging IFC, again, blazing fast, really sophisticated. Things like merging IFCs, splitting IFCs. Um, Things like color coding or interacting with it in code, we're way ahead of the game. But then, of course, when it comes to model author, can you deliver a huge hospital project or a huge skyscraper directly in IFC? I wouldn't advise it right now. It has not been solved. I mean, we've done parts of it in IFC. So, for example, I routinely look at these huge projects. I don't edit them much, but I do some editing. And if you're just doing some editing, you can absolutely do that. But if you have a team of 20 architects, 20 engineers, working on a huge project, it's not it's not there yet. But I guess that's just part of the process. It's something that will inevitably come and will be solved. I've got no doubt about it. But progress.
That's it's exciting. I would love to keep going, but we're already into extra time here. Um, and speaking of day jobs, I think we all have one of those we got to get back to at some point, right? So thank you, Dion, for your time. Thank you to everyone who joined and listened. Again, we'll send out the email automatically with the link to the video. And I feel like this was great stuff. I think there's a lot more on this topic, so maybe we can figure out a time to do a part 2 to it. There's some questions in the chat that we didn't get to. That would be fantastic for a follow-up discussion. So thanks everyone, and we'll see you at the next one. Cheers.